do is, as you read the data, you will divide by 255 so that the data is already scaled between 0 and 1. Okay? So let's pretend we've already done that, right? Now let's go to our, if we were doing it in Python, how will we do the forward pass? Our forward pass was this one. Okay. So how do we do, the next question is, how do we do matrix multiplication in Python? Okay. So using the NumPy library, there's a function available called np.dot, which does a matrix multiplication. There's one more function available in the NumPy library called np.multiply. Okay, which does an element by element multiplication, not a matrix multiplication. To give you an example, okay, suppose you have 2, 1, 2, 3, 1, 5. Here's one matrix. Here's another matrix, 4, 1, 3, 1, 0, 1. Okay. If we did np.multiply, what it will do is it will do 2 times 4, 1 times 1, 2 times 3, 3 times 1, 1 times 0, 1 times 1. So this is what the np multiply does. Okay. Can I do np dot on this one? These two? No, because the sizes are not proper. I could do np dot, so suppose this is A, suppose this is B.
Transpose.
I could do A dot B transpose. So then how will we do that in Python? You'll do np dot dot, okay, A comma B, np dot transpose. So there's a function available, transpose, np. So this will become, see, this is 2 by 3 in this example. This is 3 by 2. So what will be the answer it produce? 2 by 2. And you can always print in Python anytime. So especially in the beginning, because some of you are new to it. I know some of you are experienced Python programmers, so it's not a problem. But for the benefit of those of you new to Python, if you're not sure what it's doing, anytime you can print the shape property. So in this case, the shape will show up as 2 by 2 as an example. Okay. And once you have the shape property, you can always do shape of 0 and shape of 1 if it's a two-dimensional. So shape of 0 in this example, if I did, let's say, A dot shape of 0, what will this produce?
The
number of rows. So this will produce 2.
Yeah.
So if I did A dot shape of 1,
So
that will produce 3. Okay. Anyway, so back to our implementation. Okay, so our forward, after we have created the W1 in the beginning, right? So then in Python, your code will look something. Okay, first, very similarly, you will do W2. Okay, so same low, high, the size will be different, correct? What was the size of W2?
10 by 100.
10 by 100. Okay, same thing, you will initialize B1, B2. So, okay, and again, the size will be different. For B1, size will be 100 by 1. And for B2, 10 by 1, correct? Okay, so after we have initialized randomly the weights and the biases, then as we discussed, we will read one training data. So now let's go to the forward pass first. Okay, so this. Okay, so let's take a look at So in Python, it will look like S1 equal to, as we discussed, we want to multiply W1 with X. So what will you do? NP dot,
X, comma,
sorry, W comma. W1 comma X of whatever J. Plus, okay, if we wanted to do matrix addition, Python automatically will do that for us. So you don't have to do np.plus or np.add or whatever. Simply plus B1 will do that for you. Okay. So this will compute the S1. So now we have the S1, right? Now let's talk about how do we compute, if we are using sigmoid, how will we do it in Python?
so we define a function.
So A1 equal to 1 divided by 1 plus. Okay, Python has in the NumPy library an exponent function which will operate on the entire matrix or entire vector or whatever. So you don't have to write a loop to do one by one. Okay. So anyway, so in this case, this will
Minus.
operate on which one?
Minus S1,
Sorry,
e raised to minus,
S1.
so
Minus S1. Okay, so that will end up doing the actual computation based on the activation function. So A1 is ready, right? Now let's go to S2. S2 will become np dot W2 comma what?
A1, right?
A1 plus
Plus 1 times B2, I mean B2.
this B2, right? Now let's go to A2. A2 will become 1 over 1 plus np dot exp
S2.
minus S2.
Now calculate the loss function.
Okay, so now we can calculate the loss function. So for the loss function, let's see. Loss will be, so suppose it is 0.5 times. It was, remember, y minus a
Yeah.
times y minus a, right? Y minus a. Can I write it like this, y minus a, will it work? Okay.
Same.
Okay, the answer is no, it will not work. And the reason is like this. What's the dimension of A, sorry, this is A2, this is A2, and I should say, so let's pretend the expected output for all these 60,000 has been stored into a 60,000 comma 10. So that if I pick y of j, it will give me, so for example, let's say y of the fifth digit happens to be a 2. So what will y of 5 look like? 0, 0, 1, 0, 0, 0, 0, 0, 0. I mean, total will be 10 elements over here. So if this was digit 0, this will be 1. If this was digit 1, so this is for digit 2, and the rest are zeros. So because we have 10 outputs, right? So let's pretend as we read through the file, all these digits, we already have initialized the y array, and once I go to the computer, I'll show you how exactly will we initialize the y array, but let's pretend it already has that, right? So now my question is, can I write the loss like this? Y of j, because my loop is going through j, right? Minus a of 2. A of 2 we already computed, times y of j minus a of 2. Will this work? Okay, and this is what I was saying, this will not work, because if matrices are involved, either you have to do np.multiply or you have to do np.dot. Okay, so my question to you now is, what's the size of y of j? 10 by 1. What's the size of this?
10 by 1.
Will the subtraction work?
Yes.
Okay, 10 by 1, 10 by 1. Okay, what do we want to do to, so suppose yj minus a2 gives me these numbers like 0.3, 1.2, negative 0.5, things like that. Okay, so this is what it comes out to. Let's pretend. So to compute the loss, what do I have to do? If this is y minus a,
Take a transpose of the second one.
don't I have to square it?
Yeah.
Then square it, right? And so on. So basically what I'm trying to say is this is not a matrix multiplication. Squaring, can't you think of squaring as 0.3 times 0.3? So if this is a matrix, this is a matrix, what are we doing? Element by element.
multiplication.
So it should be np dot multiply. Okay, so this one then will become, so the loss will be computed as 0.5 times np dot multiply, and then y of j minus a2 comma y of j minus a2. Okay. So loss is done. So now the forward pass is ready. Okay, and we can print the loss if we wanted to. Anyway, we'll talk about the printing in a second.
Professor, can you go over the matrix size again, the loss one?
Okay, see, easy way to think about it is, let's say we computed some outputs, right? Some outputs over here. Suppose those numbers are 0.2, 0.4, 0.1, and so on. 0.33. Okay, these are the 10 numbers we produced in the output, the A2. Okay, loss is defined as actual output minus the expected output. And let's pretend when we computed, when we came up with these numbers, the digit 2 was fed in. If the digit 2 was fed in, then this will be the expected output. 0, 0, 1, 0, 0, 0. Okay, if we did A2 minus, y minus A2, won't it become negative 0.2, negative 0.4, and 1 minus 0.1, 0.9, and so on, and negative 0.33? So wouldn't this be y minus a? Okay, so how is loss defined? Y minus a squared. So to square it, don't you have to multiply the same element by itself? So think of this way, that negative 0.2 needs to be multiplied by negative 0.2, meaning itself negative 0.4, negative 0.4. So yj minus a2 is basically this matrix. Yj minus a2 is just, again, same data, exact same matrix. Okay, but to compute the loss, we have to do an element by element multiplication over here. It's not a matrix multiplication. So np dot multiply will allow us to do that. Okay, I forgot one more thing. The loss is a scalar. In the end, we have to add up all of these. See, if you recall, this is how loss was defined. Sum over all the outputs. Okay, so in Python, once we have a numpy array, because both of these will produce the answer. Sorry, this was wrong. Okay, this is what we are doing, the blue. This will produce a numpy array. On a numpy array, you can easily call the sum function. Okay, and that will give you the summation after doing the element by element multiplication, and that will give you a single value for the loss.
Can I use the dot function also? Or that
Here, no, because it's not a matrix multiplication. See, that's where, that's why I'm going through this. Sometimes you're using dot to do matrix multiplication. Sometimes you have to do element by element multiplication.
So if we transpose the first matrix and then multiply the second matrix, it will be the same effect.
That could also be done, that's correct, yeah. So you can do transpose of the, because this is 10 by 1, so if you did a 1 by 10, transpose of the first, then did a dot on the regular one, then it can be done. But without the transpose, you have to do NP dot multiply. Okay, so anyway, but the reason that will work over here is because in the end we expected a scalar. But sometimes, as you will see, we wanted the answer to be just an element by element multiplication, but no reduction at the end. So then you cannot do the transpose. You'll have to leave it to NP dot multiply. Okay. Anyway, so loss is okay. So forward pass is done. Now let's talk about backpropagation, meaning how will we compute these gradients, the deltas, the del's, so that we can adjust these. So if we can clarify that, then the rest of it will be piece of cake. So let me erase this part. Okay, so let's start with, as we do the backpropagation. Okay, we start with, so we are working backwards, right? We're working backwards now. So we start computing delta 2 first. Okay, so delta 2, as we discussed, was the derivative of the loss function with respect to A2, which is what? If you did the derivative of this with respect to A2, this is the loss, what will we get? 2.5 cancels?
Minus y minus a.
Minus y minus A2. So then this will be minus y minus A2. Okay, y of j, because we are in the j loop, minus A2. Okay, further we have to multiply by the derivative of the activation function, right? So derivative of this activation function is what?
1 plus
A2 times.
1 minus
minus
A2.
Okay, so my question to you is this a matrix multiplication or is this an element by element multiplication? See, if you're confused, think about it. Forget the matrices. Pretend we had individual neurons in the output, right? Okay, we did y minus a over here. Then as we go through it, this y minus a has to be multiplied by, for this neuron, a times 1 minus a. And this value will be just placed over here. Same thing for this neuron, we'll do the same thing. So it's really an element by element multiplication, okay? So our Python code will look like what? Okay, if I did minus np dot multiply, okay, y of j minus a2. Okay, so which is fine, right? This is 10 by 1, 10 by 1. So this subtraction automatically works, right? Then what should I do? A2. So this will multiply every element over here by A2, but I need one more. So I need np dot multiply again. Okay, comma 1 minus A2. And then a minus over here further. So the code for delta 2 in Python will look something like this.
Can we do the opposite also, like dot and then transpose that and convert the 1 into np dot 1? So I have a matrix of 1 or 10 rows of 1.
I don't think that transpose will work. See, it worked in that case because we were reducing it in there at the end. 10 by 1, because we have, so just focus on this part, right? Forget this for the time being. Okay, if this is 10 by 1, 10 by 1, what do we want the answer to be?
10 by
10
1.
by 1.
10 by 1. So if we did, suppose I did the transpose over here, or the transpose over here, and then did the matrix multiplication.
I still like
It will get 10 by 10, but we want the answer to be 10 by 1. See, delta 2, what are the dimensions of it? Delta 2 is the computation in the middle of the neuron. If we have 10 neurons, there will be only 10 delta 2s, not 10 by 10. So I can see anywhere you can do matrix multiplication to get a 10 by 1 answer. So anyway, it has to be an element by element multiplication. So that's why the multiply is needed. Okay, so everybody good with delta 2? Okay, let's take a look at the next one, delta 1. So now let's go to delta 1 equal to. So, okay, let's take a look at delta 1 was
Delta 2 into W2.
delta 2. Okay, first let me write it normally, times W2. And then further the derivative of the activation function, which will be what?
A1 into 1 minus A1.
Times A1, 1 minus A1, perfect. Okay, let's just focus on this part first. Okay, what's the size of delta? What do we want the delta 1 to be? How many neurons do we have here? 100. So this is, we know is 100 by 1. Delta 2, we already computed it to be what? 10 by 1. What was the size of W2?
10 by 100.
10 by 100. Okay. So again, like I said, forget this A1, 1 minus A1, which will be 100 by 1 anyway, because this is 100 by 1, 100 by 1. Okay. And this is an element by element multiplication. So, so if we don't worry about that part over here, then coming back over here, how do we get 100 by 1 out of these two?
Transpose it.
If you do the dot product,
Transpose delta 2.
Transpose W2 and then multiply it with delta 2. Okay. So if I did in Python,
Transpose it 100 by 10.
np dot dot, because this is a matrix multiplication.
delta 2,
Okay, then np dot transpose W2 comma.
That's not gonna work.
It won't work,
We want
sir.
to, you need
The
to
rows and
transpose
columns won't be
delta
the
2.
same. We have to transpose
Delta
delta
2.
2. Because it becomes 1 by 10, so the rows and columns will be the
no, that's
same.
right.
The inside number is supposed to match.
Why won't it work? Okay,
Because you're gonna have 10 by 1, 100 by 10.
Yeah.
okay.
Doing the
Won't this be, if I do the transpose, won't this be 100 by 10?
Yeah, but we can't multiply 10 by 1.
Wait, then if I do delta 2 over here,
10 by 1 again.
what's wrong with it? Why can't I multiply 100 by 10 with 10
Also,
by
now you put that to separate. Okay, that could work.
It will work. So, so that will give me 100 by 1, right? And then, see, this gives me 100 values, right? What do I have to do to those 100 values to these? Is this again a matrix multiplication, or is it an element by element?
Element by element.
Okay, so you guys get the idea. Then further you do np dot multiply. See, one of the in the one reason I wanted to, spend more time on it is, even though in the beginning you may think, oh yeah, it makes perfect sense, just do the delta, then multiply with W2, you get, further multiplication of the activation, derivative of the activation, you get everything you may seem easy. But it's so easy to make a mistake. And then literally spend, I'm not saying days, months, trying to fix the error, why it's not working, okay? So it's better to be, I highly, highly recommend as I give you the next assignment. Okay, I won't give you the code, I'll show you the code, but don't try to copy it. Because this way you won't learn as much. Only do it after you have struggled for a day and it doesn't work, then take a look at the code. But again, this is very simple. Later on, we'll be dealing with very complex networks where the convolutions and everything. I myself, first time I developed deep CNN. For 2 weeks in a row, I was debugging it. Okay, and I consider myself a pretty decent programmer, so anything I can do pretty much in a few minutes or few hours. But these can easily become a nightmare to debug. So be very patient with it. Write down neatly what we want, and then try to solve it.
Everything makes sense. Is there a way to remember when to use dot or when to use multiplication? Because that's confusing.
That's confusing. The way you can sort of remember this is, like I said, once you have a picture like this, okay, again, think of it in reality, there are, if you had, even though you're putting a single unit over here which is operating on matrices, if we needed, if the output is 10 by 1, really there are 10 neurons, right? Any computation that comes over here as we are doing the backpropagation, every neuron is keeping track of its own computation. This has nothing to do with this. So it becomes as we do the derivative of the activation function, it's an element by element on whatever came on this line before we compute the derivative on this line. Okay. However, as we go from here to find the delta, this is a full matrix over here, so that's where the matrix multiplication will come in. So once again, as you do this assignment, as you write this thing neatly, you yourself will after a while know when I'm using element by element multiplication, when I'm using the matrix multiplication. Okay. Anyway, let me now show you the Python code of how all of this looks like.
Professor, I have a question here. Why do we use the scalar for loss, even with backpropagation we are carrying?
This is just to, okay, good question. Why do we print out the loss? Even though it's a scalar and we never used it in any one of our, right? This is just to print how our network is trained. Whether it's learning or not, should we stop the training? So in the beginning, what you will see, so this is just for diagnostic purposes. It has nothing to do with the actual adjusting of the weights or adjusting of the biases. So in the beginning, you'll see the loss will be high, like 2,000, whatever, well, depending on the size of network, then it will start to go down, then after a few epochs, it will be 95, then 5.2. So you can sort of see, is it getting better? Is it learning? If you made a mistake in your calculations, what you'll see, the loss either starts to go high or never decreases. Okay. Okay. I have let me ask you one more question. Okay, if you take a look at the training of the network, what did we say? The general code is for I equal to 0 to number of epochs. Correct? Then j equal to 0 to training data. Okay, then we do the forward pass, we do the backward pass, we adjust the gradients, right? Adjust the weights and biases after we have determined the dells. Okay, so this is what the typical algorithm is, right? If you take a look at your first assignment, in the first assignment, if you recall, okay, what we did is I gave you some data, okay, and I asked you to determine the equation of the curve, which was like ax squared plus bx plus c type of curve, right? So your model parameters in this case were, in your first assignment, were a, b, and c, right? Okay, was there a double loop involved when you guys did that example?
Yes.
No, there was no. See, basically what we did is, if you recall, from the loss function over the entire axi plus bxi plus c minus y of I squared, something like this, right? So we defined the loss function, then we did partial L over partial A, partial L over partial B, partial L over partial C. Assembled these into a 3x3 matrix, inverted the matrix, and we were able to find ABC. We didn't have to iterate. This outer loop was never there. Okay, even the inner loop wasn't there because we basically summed over all the training data. So anyway, I have a friend who is in this field, and he's taken a lot of Harvard courses on machine learning, deep learning. So he's asked me a question. See, this was called linear least squares, right? Okay, so his question was, when we are doing optimization of linear least squares, whatever our model parameters are, in this case A, B, C, we can determine them exactly by solving the matrix equation. Okay, if we compare it to our neural network, we have model parameters over here, regardless the number, like W1, W2, B1, B2, right? Why can't we solve them exactly like linear least squares? Because we are doing the partial derivatives, we have a loss function. Why can't we assemble them in a matrix equation, regardless how large that matrix is, and take the inverse and find the answers for all the weights exactly? Why do we have to go in this approximate, initialize it randomly, keep updating it? Okay.
In the linear least squares, we know what we want to approximate to. In the real case, we may come across a picture that we never seen before. So,
but let's pretend we are doing regression exactly like that, because we can create a neural network to fit a model, like a square data, exactly. Okay. Okay. So let me answer that question, just in case you go for some job interview and you claim you are knowledgeable in this field.